My name is Dr. U. Salma. I am working as Associate Professor in the Department of ECE. In this semester, I am going to teach the course Fundamentals of Digital Logic Circuits. Digital logic is typically embedded into electronic devices including calculators, computers, video games, watches, etc. You come across all these appliances in your daily life. The title of the course is Fundamentals of Digital Logic Circuit. In intermediate, you are taught about circuits and you are aware of that. Then what is digital? It is the representation of some data or information in the form of digits. In this particular course, we are going to study how data can be represented in different number representation and perform specific function using logic rules. So, the design of combinational sequential circuits to perform a specific function can be done first by minimization of Boolean expressions using some techniques and implement by using the basic logic gates. The aim of the course is to provide an understanding for a student how data is represented and processed at the hardware level. This course acts as a foundation for a course on computer architecture and organization. The course objectives are the students is to be facilitated to represent numbers in different number systems, and he should be able to know the conversion of one number system to the another. The logic gates, theorems and properties of Boolean algebra including axioms, Boolean laws, etc. are to be introduced. The students with techniques for minimization of expression, that is Boolean expressions, by using Boolean laws, theorems, and simplify the expressions, and the importance of the simplification should be clearly familiarized. The design of combinational and sequential logic circuits are to be demonstrated. Coming to the Unit 1, the learning outcomes of Unit 1, the student should be able to explain different number systems. He should be able to solve different number systems like binary, digital, octal and hexadecimal. He should be able to convert one number system from another number systems. And the student should be able to perform arithmetic operations on signed and unsigned binary numbers like addition and subtraction. And he should be able to explain basic error detection methods and correction methods by like parity check methods, Hamming codes, etc. At the end of the Unit 2, the student should be able to summarize the properties of Boolean algebra, and he should be able to solve the expressions in the canonical and standard forms. And he should be able to construct the logic circuits with logic gates, and any Boolean function he should be able to implement using the universal gates. Coming to Unit 3, the student should be able to illustrate the representation of Boolean expression using K-map. He should be able to translate the Boolean expression for a simplified expression using K-maps. He should be able to minimize a given expression using Quine-McCluskey method. These are the Quine-McCluskey methods, K-map method, Boolean algebra method. These are all the techniques to simplify any Boolean expression to minimal expression. Coming to Unit 4, after completion of the Unit 4, the student should be able to explain the working of the basic combinational circuits. He should be able to distinguish the functions of different combinational circuits like adders, subtractors, multiplexers, etc. And he should be able to build combinational circuits to perform a required functions. Coming to Unit 5, the learning outcomes of Unit 5, the student should be able to distinguish the combinational and sequential circuits, difference between both of them. He should be able to explain the working of different flip-flops, advantage and disadvantage of each flip-flops like RS flip-flop, D flip-flop, T flip-flop, JK flip-flop. He should be able to design the registers, counters, like ring counters, Johnson counters, and all to perform the given function. Coming to the introduction, digital systems have a prominent role in everyday life in present technological period as ours is a digital age. So the digital circuit is one that is to built with devices with two well-defined states. The digital circuits generally the computers will take the binary will follow the binary language which is in which have two defined states 0 and 1 and some of the digital system applications are like digital computers, digital telephones, weather monitoring, control systems, etc. So the contents in the unit 1 are positional representation of numbers, general radix R system, decimal, octal and hexadecimal number systems, conversions, arithmetic with unsigned numbers, complement, arithmetic with signed numbers, different type of binary codes, introduction to error detection and error correction. Positional representation of numbers. This positional representation of numbers, if you take the expansion of original set of symbols, we can use it to represent in any arbitrary large value. That means if you consider 10 symbols in a decimal number, we have 0 to 9. So if after 9, we do not have enough symbols to count beyond 9. So the combination of zeros and nines will be will be the 0 to 9 numbers will be repeated again, but the significance will be changed by changing the position of the numbers. Suppose if you take an example, we have 0 to 9 over here. After 9, we have 10, 11 till 21 till 99. After 99, again 100 will repeat. But this time the position of the number is being repeated. So the importance of the number can be varied by using the positional representation of numbers. This is the importance of the positional representation. Now coming to the general radix R system. This is a number expressed in a base R which is having coefficients multiplied by the power R. Suppose an minus 1, an minus 2 are the numbers in the given base, then that numbers will be multiplied with the corresponding weighting factors. It is the based on the powers of the base R. So if you take an example, we can see that 4021.2, here the 4 is multiplied with the highest power of 5. Actually, we have to start from the from right to left. So it starts from 1 into 5 to the power of 0 plus 2 into 5 to the power of 1 plus 0 into 5 to the 5 square plus 4 into 5 cube. And the point which is there, from there onwards, we have to start from the left to right, that is 2 into 5 to the power of minus 1. This can be clearly explained in the conversions of one number system to the another number system clearly. Here, we just want to explain the importance of the general radix R system. So how a number can be shown in terms of a decimal number is being shown, and the importance of the numbers with the multiplying with the weighing factor is being explained over here. Now coming to the decimal, octal, hexadecimal number systems. This is the name of the systems because we have 4 number systems. We are considering decimal, binary, octal, hexadecimal. And the radix R, that is the base value of the number system. The base value of decimal is 10. For binary it is 2, octal it is 8 and 16. Generally the the highest number is R minus 1 and the lowest number will be always 0. So for 10 radix R, which is equal to 10, we have 0 to 9, 0, 1, 2, 3, 4, 7, 8, 9. For binary, it is 0, 1. For octal, it is 0, 7. For hexadecimal, we have totally 16. To represent 16, we have already used a symbol 0 to 9. So beyond that, we are representing, we can't go 1, 0 because it should be represented by a single digit. So instead of 10, we are representing it as A, B for 11, and so on till F, and F represents the 15. So 0 to 15, totally we have 16 over here. So next is decimal system. What is the importance and application of these number systems we are discussing over here? Here the decimal system. Every day, money, weight, length, etc. Whatever it may be, whatever we have dealing in the real life, that is done in the decimal system. These are all dealt. So decimal numbers are the situations where more precision is required, whereas whole numbers cannot provide. So whole numbers, we cannot completely depend on the whole numbers in the daily life activities, because there should be a more precision, and we need to go for the decimal system. Coming to the binary number system, this number system is found in computer technology, where we are associated with two-digit number, that is 0 and 1. Coming to octal number system, this is widely used in Linux and Unix file systems, and it is used where there is a support for hexadecimal systems. Coming to hexadecimal number system, hexadecimal number system is to write large numbers in few digits. We can represent a large numbers in few digits by using the hexadecimal system. And also the hexadecimal systems, because of less number of digits, the error occurring also will be reduced. So that is the advantage of the hexadecimal systems. So these are the four number systems which we have, which we are discussing in this unit. So coming to the terms for the binary code size, these are the different binary terms where we have the bit. Bit means it is a just a unity representation. It is only one size, one bit. Bit is one bit means we have only one unit. It is single bit representation. And nibble. Nibble means it is 4 bits. Byte means 8 bits. Words means 16 bits. And double means 32 bits. This is the size of each and every term which we are using in our binary code. Now, coming to the conversions. Conversions of decimal to any base. So, actually, when we are considering, as is the initial starting for the conversions topic, I need to separate conversion. First, we are going to discuss the conversion of decimal to any base. In that part, we are going to discuss the first one is without fractional part. Next comes only fractional parts. The third one comes both fractional point with the fractional, a number point with fractional. That we are going to see in the third one. Let us see for the A, numbers without fractional part. Here, in this, 2 is divided with 456 is divided with 2. When we are giving a decimal number and we are asked to convert in terms of binary. So for binary, you need to divide the given decimal number with the whatever is asked. Here binary is asked, so we are dividing with 2. So 2 is dividing the 456 and we are getting 228 and we don't have any remainder. So that is 0. Again 2 is dividing 228, we are getting 114, that we are getting it as 0. Again 2 is dividing 57, again 0. So till here we did not get any remainder, and from here onwards we are, if we are dividing 57 with 2, you are getting remainder as 1 and 28 is left over. Again we are dividing with 2, 14. Similarly, you have to go on doing till you get the value of 0 at the end. That, and from the bottom to top, we are going to write down the answer. So we will start from the bottom level, 1 1 1 0 0 1 0 0. This is the answer for the 456 base 10 in terms of binary. So that is the answer. This is how we will do. So the second example, if you go for the second example, here binary is over. Now we came for the octal. So octal means whatever the number we are having, which is asked given in decimal, and when you are asked to convert in other base, that number can be divided. That number is used to divide the given decimal number. So 8 here. So 8 is dividing 87. We got the remainder as 7. And 8 is dividing the 10 again. We got the remainder as 2. And 8 is dividing the 0. And we got it remainder as 1. So that is, and again we are going to write the answer from bottom to top, that is 127, 127 base 8. Similarly, the same procedure has to be followed for the hexadecimal, where 152 base 10 is given and it is equivalent, we should make it equivalent to base 16. So again we are dividing 16 with 152. We got it at 88 and the answer is 88 base 16. So that is over. So we have done the numbers, decimal number without any fractional part directly for other conversions. Now when we are given a decimal number with only fractional part, then how we are going to start the procedure. So for this, what we will do is, we will take the 0.8125 and you will multiply with A2, because we are asked for base 2, we had to multiply with 2 and we got the answer as 1.6250. So whatever the number in front of the point, before point, generally it will be 1 or 0. That number has to be put at the side as shown over here, that is 1. So it should be put in the right side, dash 1. And the number which is in the fractional part, that is 0.6250, that only has to be again brought to the left side and you have to multiply with 2 again. Again this time, again we are getting some 1.250. So 1 is coming in front of point. So that number again has to be placed at the right side. And again we are multiplying the 0.25 part only. The fractional part is being brought at the left side and we are multiplying with 2 and we get the 0.5. Here at this time, here we did not get any 1 over here. We got just 0 point. So we will write only 0 at the right side. Again the 0.5 is being multiplied to 2 and we got it 1 and we are putting over here. So the answer is, and we are not going to disturb this fractional part. So the answer also will be written like 0 point. The answer is, question is 0.8125 and answer for in the binary form also will be 0.1101 base 2. So in this type of problem, we will be writing the answer from the top to bottom, not from bottom to top. So 0.1101 base 2. Okay. And example 2, if you go for the next example. So here 0.862 base 10 is equal to base 2. So what happened is, we multiplied with 0.862 with 2. We got it as 1.724. It is again base, again the 1 is there in front of point. We are putting it over at the right side. Again we are taking the 0.724 and multiplying with 2 and putting 1. Again we are getting the same way it is been repeating. And what happened is, at in the first problem, we just simply got 0.5 into 2 at the 4 steps. But even if we are going beyond 6 steps also, we are not sure that the problem will be having will be ending, because it is recurring. The answer is being recurring over here. So what happens is, we have to stop at particular 6 or 7 steps. When we are in doubt that the problem will not end, there we will stop and we will write the values 0.1100111. This is what we have, and we can just put a dots like that, such that the problem is not completely ended. That indicates, the dots will indicate that problem is not completely ended, but we can stop the problem and we can write down the result. That is the example 2. Now coming for the example 3. Now again this is 0.2968, which which you have to make it equivalent to 8. Again you will follow the same procedure, and then in the end also you did not get the correct exact value. You can stop at the 8th or 9th step and just you can write 0.2277542 dot dot 8. It is enough, and you can write the result from the top to bottom. Okay, that is regarding the numbers with only fractional part. Now coming to the decimal numbers with fractional part to any base. That means earlier it was without fractional part, with only fractional part. Now we are putting both the fractional and non-fractional part. Okay, so now we have like this 25.012. So what we will do is we take 25 separately, 0.012 separately, and we'll try to perform the same procedure what we have done earlier. So for 25, we go on multiply with, we divide with 2, and we will get the result like this 10, and from the bottom to top you will be writing the answer 11001 for this. And for 0.012 you have to multiply with 2 again. You got 0.024, you got 0, again you will multiply with 0.024, again you got 0. So similarly, but in this you got you're getting all zeros, we are getting all zeros, and we have to do till we get some value 1. So this has been repeated until 1, the steps are being repeated and the answer is being written. So what happens is the answer is 0.000 after how many? 3 6 zeros 1. We got it as like this. So now we are going to club the both the answers. So 25.012 base 10 is equal to 11001 point all the zeros 1 recurring 2. That is what we have got. This is how we will to perform any decimal number, to perform a given decimal number to any base. It can be 8 or it can be 16 or it can be to any base you can do it. So same if you do it for the for base 8 also, what we will do is for 49 we have taken separately by dividing by 8, and which is not a fractional part. And now if we take the fractional part, we have taken the 0.21875 and that we multiplied with 8 and we got the answer. This is how we did it separately for both, and later on after getting the results we have clubbed it and we have put it in this way. Like in this way, in this the fractional part for base 8, 0.21875 into 8, 1.75 is obtained, and when we multiply with 0.75 into it, we got exactly 6. So there is no need to go for the other step. We can stop over here and we can write down the answer. So the answer for 49.21875 base 10 is equal to 16.16 base 8. This is what we can say. And next is third example, 567.1875 base 10 is equal to base 16. So again here also we are going to divide with 16 separately and we are going to multiply with the fractional part with 16, and we got it exactly 3. So we are putting the clubbing the answer and putting over here. This is how we can convert a given decimal number of any type for any base. This is the methodology for this. And next, if you go for the second one, that is B, conversion of any base to decimal. When we take this binary to decimal, we have this, what we will do is, we will take, here I have considered both fractional and non-fractional part, both are mixed over here. For this, what we will do is 101, if you take it, the procedure to solve a binary number to base 10, earlier in the earlier method, we have divided. Here we are going to multiply with the multiples with the power of 2's. We will start from right to left. So we will start 1 into 2 to the power of 0 plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 2 square. That means we are starting from right to left. So that's again from the starting with the power of 2 as 0. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Like that we are going to start, and the answer we will add all, will multiply, we will add with the, will multiply with the corresponding powers of 2, and then we will later on we will add and we get the answer as 5. Similarly, if you take the for 0.1101, what happens is from for this problem you need to go from left to right, left to right. So 0.1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2 plus 0 into 2 to the power of minus 3 plus 1 into 2 to the power of minus 4. Has our number scale is there now, how that 2, 1, 0, minus 1, minus 2, minus 3, minus 4, how it comes, that way we have to write down. We have to go from left to right. So after that, you multiply it, you will get it as 0.5, 0.25, 0, 0.06. And if you combine it, multiply and add, then you get it as 0.8125. After getting the results separately, then you can both combine and write in the answer. So we got for 101 we got it as 5, and 0.1101 we got it as 8125. So 5.8125 is the answer for the binary number which is converted to decimal number. That is what. So next one is octal to decimal. Binary to decimal is over. Now we are going for octal to decimal. In this also we will follow the same procedure, but instead of 2 we will be doing for 8. So 127 base 8, 127 base 8, you have to start from where? From right to left. So you start from 7 into 8 to the power of 0 plus 2 into 8 to the power of 1 plus 1 into 8 square. So similarly we will do it and we'll get the answer in this way. Next one. Next, hexadecimal to decimal. If you take the example, f9 base 16 is equal to 10. So again we have to start from right to left. 16 to the power of 0 into 9, 16 to the power of 1 into 15. So that is the answer. And similarly, if you do it for when you have the integral part also, we can follow the same. You multiply with 3 into 16 to the power of minus 1. 237 base 16 is the same how you got it from by multiplying 16 power 0, 16 power 1, 16 square. So that way you get and combine the answer and write down. This is the way how we convert the given any base number to the decimal. Now the third one is conversion of any base to binary. If you are given any base to binary. Already we have done the decimal to binary and binary to decimal is over. So we can we need not consider the decimal. Already the interconversion, mutual conversions has been done. So we are not considering decimal over here. Just we are considering octal to binary and binary to octal to binary and hexa to binary. That is what over here. So example is given. 127 base 8 is equal to base 2. So how you are going to convert? So for this we should take each and every individual number of base 8 separately. We take first, let us take 1. 1 you have to represent in the form of 8421. 84, so it is octal, na? So we will go for 421. That means 421 representation. So what happens is 1 is equal to 0 into 2 square plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 0. As it is 1, we consider only the first one and remaining are zeros. Again, if you go for the 2, the middle one will be the 2. So we put 2 to the power of 1 into 1 plus either side 0 into 2 to the power of 0 and 0 into 2 to the power of 2. And for 7, when we add 4 plus 2 plus 1, that is 1 into 2 square plus 1 into 2 to the power of 1 plus 1 into 2 to the power of 0, it is equal to 111. That means for octal we have to consider 4 to 1 representation. So when we consider 1, only the 1 is enough and remaining are zeros. So we are considering only 1. So that will be 1 into the power of 0 and remaining are zeros. When we consider 2, the middle one 4 to 1, 2 is to be considered and remaining the either side can be 0. So that is why how we have put it as 0. Coming to 7, when we multiply 1 into 2 to the power of because we need all, because 4 plus 2 plus 1 we had to add all and we had to put it as 111 base 2. That is how we had to convert the given octal number to binary. And coming to the second example, that is 6342 base 8 equal to 2. For this what we will do is 6 means 6342. So again we need 4 to 1 representation. For 6 we can have like 1 1 0. 1 1 0. 1 is multiplied with 2 to the power of 2 plus 1 into 2 to the power of 1 plus 0 into 2 to the power of 0. That means if you that in that form we have to consider. Otherwise we can see go for simply 4 to 1 notation. That means 6 plus 4 plus 2 is equal to 6. 110. 3 we can take it as 0, 1, 1. 4 we can take it as 100 and 2 we can take. After getting the whole, all the individual binary representation for octal, then we can put all together and write down the answer. That is how means we have 6342. For 6 it is 110, we put it as 110. For 3 it is 001, 011, we have put it over here 100, 010. So this is how we got the answer. So for octal we need to go for 4 to 1 notation because the maximum number for octal is 7. 0 to 7. 4 to 1 is the highest. 7 is the highest number. So 4 to 1 means we get 111. So conversion of any base to binary. You continued. In this also, when we have 2673.54 base 8 is equal to base 2. So again here separately we have the what we have is fractional part also we are considering over here. For this also fractional part also we have to follow the same procedure. There is no any difference between this without and with fractional part. Both are having same procedure when we are considering octal to binary. And here also what happens is 7 means it is triple one, 6 means 110, 5 means 101, 4 means 010, sorry 100, 3 means 011, 2 means 010. This is the 4 to 1 representation of the individual numbers. After doing individually, then after getting the answer, we have to combine all the answers to get the final result. So what happens is 2, 3 for 5, 4 it is 1100. So what happens is when you're writing it, you have to write down the numbers how it is in which order we have to put in the same order. For 5 it is 101. For 4 it is 100 after point that we have put over here. Whatever the order is given in that order only you are going to put the binary numbers after the conversion. So next hexa to binary. Hexa to binary 79 base 16 is equal to base 2. When we take like this 79 for 9 it is, how can we write for hexa to binary? 9 means it is base 16. So we can have the maximum number from 0 to 15. So for 9 what we have to do is for hexa number, earlier for octal we took it for 4 to 1 representation. When we consider hexa, we have to take 8, 4 to 1 representation. So like this we have, and now for 9 we can represent 9 as 1001. For 7 we can represent as 0111. So when 79 base 16 is given, after putting the numbers in order, binary bits we get in this form. The result is in this form. That means for a hexa number or octal number, if any digit is more than the, if for example, if you take octal number, if any digit is more than 7, then it is not a correct number, octal number. Similarly, if you take for hexa also, if the number is more than, generally we don't get for 16, for binary octal we get the same one. So conversion of any base to binary. Any base to binary. So again for F9 16 is equal to base 2. So for F means it is considered as 15. So what we will do is for 15 we have the binary digits 8421 notation, it is 1111. For 9 it is 1001. Later on you will combine and you will put it over here. Again for example 65D.616 base 2, if you are having in this way, again you will do it separately and you will do it and you will put it in that particular order. And similarly the C69 base E point E base 16 is equal to base 2. Again all that we will be doing it individually and then we are putting in the combined form in the particular order. That is how we will do for the conversions. Now octal to hexa. Now that part is over from octal to binary and octal to hexa to binary. Now we are going for the next one, that is octal to hexa. how we will convert the octal to hexa. Then what we will do is, for this we don't have any direct method. Again we have to go to the indirect method, that is converting octal to binary, again from binary to hexa. That is what we have to do. So 3267 base 8 is equal to 16. So now you convert the 3267 in the form of binary. So 7 can be written as 111, 6 can be written as 110 because we are following 4 to 1 notation. 3011 to 010. 7 already I have explained you how we get 7. 111 for 7. 7 means 4 to 1. 4 plus 2 plus 1. 6 means 4 plus 2. 3 means 2 plus 1. And that is 011. 2 means 010. So we have done in this way, and we are combining it and we are writing. After combining, we get, after combining, what we will do is, now we will separate this one for 4 digits. We will separate, or otherwise will group for 4 digits. We have to start it from the right to left, not from left to right. From right to left you have to start. So first start trying to make group of 4 bits. So 0 1 1 1, and after that 1 0 1 1 0 1 1 0. So now after making group of 4 bits, then you try to again convert that group, each and every group, to hexa number. So the first group is 0111. 0111 means it is 7. Then next 1011, it is B. Next 0110, it is 6. So 6B 7 base 16. Next hexa to octal. Again we have to follow the similar method, that is indirect method, to convert from hexa to octal. Hexa to octal. So what happens is, F, 4 F's and A. F means nothing but 15. So for 15 you have to find out this binary number. That means all ones, 4 ones, 8 4 2 1, 4 ones. For A it is 10. 10 means it is 8 plus 2. That means 1010. That is how you get. After getting it, what you will do is, again you will put all the binary numbers in order of your given problem. So 1 1 1 1, like that you go on putting. So now this number is asked you to convert into, you are required to convert the 16 into base 8. So in previously for base 16 you have grouped for 4 bits. Now you have to group for, because it is base 8, you have to group for 3 bits. Again you have to start from the right to left. So what happens is 0 1 0. Why we are doing for right to left means, you can add zeros at the left side. We cannot add the zeros in the right side because it will increase the value. It will increase or change the value. We cannot add at the right side. So whatever you want, you can do it at the left side only.